Einstein's relativity theory. Einstein's theory of relativity revolutionized the way we understand space, time, and gravity. It consists of two major components, special relativity and general relativity. Each plays a crucial role in reshaping classical physics, offering a new framework for understanding the universe's structure and the behavior of objects within it. Special relativity, published by Albert Einstein in 1905, focuses on objects moving at a constant speed, particularly at speeds close to the speed of light. It introduced the groundbreaking concept that the laws of physics are the same for all non-accelerating observers, and that the speed of light in a vacuum is constant, regardless of the motion of the light source or observer. One of the most famous outcomes of special relativity is the equation E equals mc squared, which shows the equivalence of mass and energy. This equation means that energy and mass are interchangeable. Mass can be converted into energy and vice versa. Special relativity also led to the realization that time and space are not absolute. Instead, they are interwoven into a four-dimensional fabric known as spacetime. Time dilates or slows down for objects moving at speeds close to the speed of light relative to a stationary observer. This phenomenon, known as time dilation, has been confirmed in numerous experiments, such as with atomic clocks on fast-moving jets. Similarly, space contracts in the direction of motion for fast-moving objects, a phenomenon called length contraction. Another key concept from special relativity is the relativity of simultaneity. Events that are simultaneous for one observer may not be simultaneous for another observer moving at a different velocity. This challenges our everyday intuition but has profound implications for our understanding of time. General relativity, developed by Einstein in 1915, expanded upon these ideas by incorporating acceleration and gravity. In this theory, Einstein proposed that gravity is not a force, as described by Newton's laws, but rather a curvature of spacetime caused by mass and energy. Large objects like stars and planets warp the spacetime around them, and this curvature tells objects how to move. The more massive the object, the more it warps spacetime, and the stronger the gravitational effect. One of the most well-known consequences of general relativity is the prediction of black holes, regions of spacetime where the gravitational pull is so intense that not even light can escape. Black holes are formed when massive stars collapse under their own gravity, compressing their mass into an infinitely dense point called a singularity. The boundary around this point, known as the event horizon, marks the region beyond which nothing can return. General relativity also predicted the bending of light by gravity, an effect called gravitational lensing. This occurs because light follows the curved paths in the warped spacetime around massive objects. Gravitational lensing has been observed in many astronomical phenomena, such as the bending of light from distant stars by galaxies or galaxy clusters, providing strong evidence for general relativity. Another confirmation of general relativity came from its prediction of gravitational waves, ripples in the fabric of spacetime caused by the acceleration of massive objects, such as merging black holes or neutron stars. These waves were directly detected for the first time in 2015 by the LIGO Observatory, a century after Einstein predicted their existence. This detection further solidified general relativity as a robust description of gravity. The effects of general relativity are not only relevant in extreme cosmic conditions but also in everyday technology. For example, The Global Positioning System, GPS, relies on highly accurate timekeeping by satellites in orbit. Due to the combination of their high speeds, special relativity, and their distance from Earth's gravitational field, general relativity, time runs slightly faster on the satellites than on the ground. Without corrections based on Einstein's relativity, GPS systems would accumulate errors, leading to incorrect location data. Both special and general relativity fundamentally altered our understanding of the universe, challenging long-held assumptions of Newtonian physics. Special relativity replaced the idea of absolute space and time with spacetime, while general relativity provided a new description of gravity as the curvature of spacetime rather than a force. Together, these theories have been validated by a range of experiments and observations, from particle physics to cosmology, and continue to influence the fields of theoretical physics and astrophysics. Einstein's relativity theory has not only advanced scientific knowledge but also inspired philosophical debates about the nature of reality, space, time, and existence itself. While quantum mechanics governs the microscopic world, relativity governs the macroscopic and cosmic scales. Efforts to reconcile these two great pillars of modern physics into a unified theory, sometimes called quantum gravity, remain one of the most significant challenges in contemporary science. Nonetheless, Einstein's theory of relativity remains one of the most profound and successful scientific theories ever developed, providing a deep and lasting insight into the workings of the universe.